So the first talk is by Martin Brevenbohr, Relational AI. The title of the talk is Building Declarative Data Apps with Relational AI. And I apologize in advance if I say people's names wrong, but take it away, Martin.
All right. Hi, everybody. Welcome. So I'm going to talk today about Relational AI. There are a couple of talks already online available about our system. So I'm actually mostly going to show how you use it and what you can achieve with it. If you want to know more about the internals, go watch the other talks. Yeah. I do need to say briefly what we actually do. So we built a database system. It's for intelligent data apps. We'll get into what we mean by that. And they're based on relational knowledge graphs. So think of it as knowledge graphs in a relational setting. So we intend to support a few target workloads, reasoning, graph analytics, machine learning optimization. So that's the space where we're in. Yeah. So now this is all based on a few innovations that make it possible to run graph workloads on relational systems. In particular, our joint algorithms and semantic optimization. This is work that we do together with people in academia, in particular Dan here. It's very exciting. But if you want to learn more about these items, go to the other talk. Yeah? Okay? All right, so what I wanted to do today is to show like how you could build an application, and we're just going to pick flight data as an example, and we're going to see like what is actually intelligent about these applications and how does that utilize a knowledge graph. So like if you think about what could be smart about a flight data application, you could think of, let's say, analyze the performance of carriers. You might want to know which ones are slow. You might want to know which aircrafts are bad. You might want to discover relationships between time of the day and delays. You might want to plan something, like where's my next maintenance station going to be. You might want to discover historical trends and so on. Yeah? So that's what we're going to operate on. Now, if you look at this in a cloud data warehouse, then you typically get something like this. And this data set really lacks information for a tool to operate on this data effectively. Like if you know the schema, maybe you can work with it, but if you don't know the schema, there's really very little you can do with this. So to give you a few examples, so these are flights, right? There is a flight here that was canceled. You see that there? That's the yes. And the flight time of this is 0. So now imagine that you do an aggregation over this and you're computing the average flight from here to there, and you forget about this canceled flag. Suddenly that's a very quick flight. And so your aggregation is wrong. Yeah? Another example is that there is a flight time here, but it doesn't say this. Is this minutes? Is it hours? Something else? And then there's a distance. Is that a kilometer? Is that a meter? And so on. Yeah? So this is very challenging to work with. So we're going to try to make a better model. So this sketches out the basic model here. But we're in our system, in a language that we call REL, we're going to model these things better and define clear concepts that the tools can work with. Like, for example, we very clearly define what a heliport is. Those are very different properties. So you might immediately want to exclude that from certain queries and analysis that you're doing. We're going to define exactly what a canceled flight is. We're going to define exactly that an arrival delay is a minute. Yeah? And if we're doing anything with, let's say, kilometers or minutes or whatever, then we're going to use specific units of measurement to make sure that we know exactly what we're talking about. So let's say the coordinate of an airport is in latitude, longitude, elevation, and we will know exactly what the units of these are. I'm not going to explain this in detail. Hopefully it's just kind of intuitively clear roughly what this stuff means. Yeah? All right, so next we also care about the data integrity. So we want to make sure that once the data is in the system, that the data actually stays correct and follows a schema. So for example, what you can say is that like if you have an origin of a flight, that needs to be a flight and an airport. It can't be something else. A flight needs to have an origin. And you can have only one origin for a flight. If you are cancelled, you cannot not have a flight duration. And a flight cannot be cancelled as well as diverted as well as arrived, let's say. Yeah? So next we can do all kinds of fun aggregations. And these now become more likely to be correct because we have defined these concepts already. So we can count the number of flights. In this data set, there are 30 million. We can count the carriers with the most flights. Apparently that's Southwest. We can count for the carrier. We can compute the mean aggregate for the average delay by carrier. So apparently that is AirTran, which is defunct now. Atlantic Coast, which is also defunct. And next is United Airlines. So I think they should be a little bit worried about being next in line here. And apparently Hawaii is great. Yeah. You can also figure out, like, let's say, what is the ratio of canceled flights per airport? And apparently that's Unalaska, which is in a corner of Alaska and probably has really bad weather or something, I would guess. But I didn't check that, okay? All right, so now we can add reasoning. We can add stuff to the system where we can derive new edges or knowledge in the graph. So we make located intransitive. So let's say if A is located in B and B is located in C, then A is also located in C. We're going to compute the airport distance, and we're going to do that correct. So we're going to compute that with like the radius of the world and units of measurements, and we're not accidentally multiplying kilometers and miles and that kind of stuff. Yeah. And then we can also use all kinds of library abstractions of things defined in REL itself. So for example, in REL you can write an abstraction for shortest path length. So that's not a library that you call in Java or something like that, that is defined in REL, in our language. And then you can, let's say per carrier, determine how many steps it takes to get from here to there, and we'll get back to that. Yeah? All right, so next schema abstraction. So in typical graph systems, you really want to query the graph and actually understand what the type of nodes and the relationships in the graph are. So we support that, even though REL is not a dynamic language, but the schema appears logically as data, and that means that you can query it, basically. So, for example, you can ask for like the count of all nodes in the graph. That's kind of obvious. I suppose that you want that, and you get 38 million. You can also ask for the count of all nodes grouped by type, and then you get, let's say, flight, aircraft, and all that. So notice that now here the type is really schema, but we're treating it logically as if it's data, and that's why we can write these aggregations over it. Yeah? All right, so next let's actually query the entire schema. So we're just going to make a different graph, which is the graph of the schema of this graph that we're working on, yeah? And that's defined here. Forget about the details. And then we're going to show that in Graphis, and then we get this picture that I showed earlier. So the picture was actually generated from the actual system, basically, yeah? Okay. So now you can, because we have schema as data, you can also compute all kinds of stuff over the schema that you normally would apply to data. So let's say at the schema level, you can say, like, how do I get from flight to state? If you want to find a connection in your graph and you want to know how to traverse that graph, you can ask that. You can ask for the actual shortest paths between those 2 points, and then you get the description of the nodes that you get. You can also ask for all the acyclic paths, and it's a very long list, of course, so I stopped there at some point. And then remember that these graph algorithms are actually written in REL, and they're optimized with our system and with the algorithms that we're working on. Okay, so you can express graph analytics like PageRank as shortest path. And so what this shows here is actually a map that is generated in REL from geodata. So we actually import the maps into the system. So this is not a picture or something. We do PageRank over the root graph. We determine, let's say, for example, that Atlanta is a very central node. And in New York, there are some central nodes there. And then we compute all the shortest paths between those places. And apparently, between these 2 airports, you have to transfer it twice to actually get anywhere. Yeah? So this is exactly what we're trying to achieve, is that you can very easily express very complicated algorithms and analyses. And because these are actually defined in REL, you can do variations as well. Like everybody has PageRank, it's kind of boring, right? But you can define your own variations or different analyses that you need. Okay? Now, so to expand on this, in data science, you want to understand your data well, typically. So let's say that you have a data set that you imported. You want to be able to understand the statistics of it. Data scientists, for example, use a function describe for that you give it a data frame and you get stats for it. So let's describe airport. This is, again, in relational system, right? And describe is defined in REL itself. And then you learn, for example, that the maximum airport is 12K feet. That's kind of interesting. I was surprised by that. It's very high. It turns out that that's actually a heliport, right? So that's in Colorado. And now if you want to restrict it better, you want to say, like, oh, give me the highest actual airport. Then you get 9K feet, which is Lake County. They're very proud of that. I searched for it. Their website says highest airport in the United States. So, yeah. Okay. All right. So that's what you can do. And then finally, we have relational machine learning. So basically, what we do is that we don't farm out to other machine learning libraries. We actually run all the aggregations and the training that is needed for the machine learning within the database itself using our relational algorithms. So to sketch, this is really hard to explain how it works exactly, but to sketch how it works, like this is basically the definition of a linear cost model. It's very simple, of course, but you can define that in REL. You just write down the math for how to compute the error of a linear regression, and then you can train that with a minimize function that takes the derivative of it, which again is REL, and then you can do your training over an example data set. For example, you could find out the correlation between the arrival of the day of the flight and the delay that you can expect. And there is actually a real correlation. So if you arrive in the evening late, then you have a high chance of very long delays. So, yeah. All right, so like I said, there are other talks that go more into the system properties. So if you want to learn more about it, I would particularly go to the CMU talk. That's probably the best one. That's the best system overview. There's also one that goes more into the semantic optimization. And anything we are presenting will end up on our Twitter. So if you follow that, then you'll see the talks there as well. All right, questions?
So how do you ingest data in this database, and is there like a efficient way to do it?
Yeah, it's a very good question. It's very interesting. I hope to get into that more in the future. So our system is extremely scalable, and in the graph representation. So let's say you can take a CSV file or a JSON file, or let's say CDC from Snowflake or something, and we actually present it as a graph. So your CSV file looks as a graph, and then in the language you can map that into the knowledge graph that you want. So initially you have a low-level representation of the data that you're ingesting, and very high level you map that into what you want to have. We have examples on the website. So yeah.
So I have a question from the stream, the Zoom stream. Do you update the original data set based on the semantic constraints provided, or is it mainly a query language?
So it depends how you use the constraints. So we have different types of constraints. The ones that I show here are integrity constraints. So let's say if you import data that violates the constraints, we'll say, no, you can't do that. We also, these integrity constraints are also used by the semantic optimizer to then, let's say, optimize the query that you're running. We also have soft constraints, so let's say you can install them and get statistics out of it or something like that. That's not what I showed on that slide, so yeah.
Can you also support some kinds of prescriptive analytics?
Yes, we can, yeah. So I didn't have time to get into that, but we support optimization methods and linear programming and all that. And so in the same constraints, just like in AMPL, let's say, you can actually write the constraints that you want to solve for, and then we give you the optimal solution with that. So that's supported as well, I just didn't get into it, yeah.
So one more question from the stream. Thank you for the great overview. I'd love to hear more about what you consider the hardest open challenges that should be addressed next.
That's a good question. Well, so I think it's mostly probably the split brain that's currently happening. So let's say databases, many databases out there, they are really good at storing your data, and they try to do as limited as possible otherwise, right? You can query out your data, let's say, but you can't express any complex computation in it. That's supposed to be on the client. And I think that's kind of harmful. It's understandable, but harmful. And basically what we're trying to do is to let the data management system support more complex computational workloads and make that scale and reliably perform. I think that's a big challenge. But it's also kind of almost necessary, because if you have a split brain with a client application, then the database system cannot optimize for the workload that's being run. It cannot predict what you're doing next or what you're querying next very well. So I think that's the biggest challenge. So.
Well, thank you so much.
All right, thank you. Thank you very much.